Albrecht. I'm an assistant professor at the University of Edinburgh. And this work was done at 5AI, which is a UK-based company building self-driving vehicle technologies. In this work, we're interested in prediction for autonomous driving. And there's a few things we require from prediction. Prediction should be sample efficient, probabilistic, and multimodal. And in particular, we're interested in having prediction over flexible timescales, because planning usually operates on flexible timescales. And importantly, we want prediction to be interpretable, which means that we can make sense of why certain predictions were made, and furthermore, so that we can try and explain and justify how the predictions influence the decisions of the ego vehicle. Here's an example of a scenario and the kind of prediction that we want. There's a blue ego vehicle approaching a junction from the south, and its goal is to turn left towards the G1 goal. There are two non-ego vehicles, one coming from the left and one coming from the right, which has stopped. In this situation, we want the ego vehicle to understand that vehicle number 2 is most likely intending to turn towards G2, because it would have been irrational for it to stop if it wanted to go straight or turn to the left towards G4. Moreover, we want the ego vehicle to understand that vehicle 2 will continue to be stopped until all the oncoming traffic has passed, because only then can it execute the turn maneuver in a safe way. So this then leads to the realization in the ego vehicle that there is a window of opportunity to enter the junction and turn left while vehicle 2 is waiting. And this whole chain of reasoning is the kind of sophisticated prediction that we want from the system, and also we want to be able to interpret these predictions just in the way as I explained. So in this paper, we make a step towards in that direction with a method called Interpretable Goal-Based Prediction and Planning, or IGP2. The approach is this: in order to predict the future maneuvers of a vehicle, we must understand why or to what end it executed its past maneuvers. So the realization is that maneuvers are a part of a plan to reach a goal, and if we can recognize that goal, then we can predict the trajectories to that goal under variable states and timescales. We make 3 main contributions. First, we show how to do goal recognition and multimodal trajectory prediction using a method called rational inverse planning. We then integrate this method with Monte Carlo tree search to generate optimal plans for the ego vehicle. And then we evaluate the full system in simulated urban driving scenarios, where we show that we can achieve robust and accurate goal recognition. That goal recognition leads to improved driving efficiency measured by driving time. And importantly, that we have the ability to interpret predictions and to justify the ego vehicle's decisions. This is a high-level overview of the IGP2 system. There are 3 main parts: as a plan library, goal recognition, and ego planning. And over the next few slides, I'm going to tell you about each, starting with the plan library. The plan library has 2 layers. First, we assume that at each given time, a vehicle is executing one of a known set of basic maneuvers. For example, a lane follow, lane change, turn. Each basic maneuver specifies applicability and termination conditions and gives a trajectory, which is a reference path and the target speeds along the path. On top of the basic maneuvers, we define macro actions, which concatenate basic maneuvers using context information such as the static road layout. Here you see an example for the exit right macro action, which concatenates 3 basic maneuvers. First, lane follow until we get close to the exit point. Then we do the give way maneuver, which slows down and checks for priority traffic. And if things are clear, we switch to the turn maneuver. So by using sequences of maneuvers like this, we can keep the planning or search depth in MCDS planning and goal recognition shallow, which makes the processes a lot more efficient. Next, we have the goal recognition part. First, there are 2 things that we assume are given. We assume there's a module which can detect the currently executed maneuver of a non-ego vehicle. And also there's a module which gives us a set of feasible goals for the non-ego vehicle. So in this case, it would give us the goals highlighted in red for the vehicle 2. We can then use inverse planning to compute probabilities over the goals for a non-ego vehicle. And this starts with the assumption that each non-ego vehicle plans to reach one of its goals using the macro actions we defined. And we compute these probabilities using an application of Bayes' law. And the first line here, you see a straightforward application of Bayes' law. This is the probability of a goal given a sequence of observed world states. And the interesting thing is how we define the likelihood. This is the likelihood of that sequence of world states, assuming that the non-ego wants to reach this given goal. This is defined as an exponential function of the difference of two reward terms. On the right, this is the reward for the optimal plan for the non-ego vehicle from the first time when we first detected it. So this is the best possible thing it could have done to reach that goal. And the reward term on the left is the reward for the optimal plan from the current observed state to the goal. So after the trajectory that we've observed so far, and then planning optimally onward. So the term on the right can be viewed as an upper bound. It's the best you can do. And the idea here is that the closer these two reward terms are, the more rational the observed driving behavior is for that given goal. And so that will increase the likelihood and vice versa. And these reward terms are computed using A star search over open loop macro actions. Next, we have the ego planning part. In ego planning, we want to maximize this formula here. This maximizes two things, basically. First, it maximizes the probability of executing a trajectory that achieves the goal. And secondly, we maximize the quality of these trajectories. And quality here is quantified using a reward function, which is a linear combination of reward components like trajectory execution time, longitudinal and lateral jerk, path curvature, and distance to leading vehicle. So this is a standard approach. In our work, we use Monte Carlo tree search over closed loop macro actions. This is the pseudocode you can find in the paper. And I'm just going to go through the main blocks in this pseudocode to give you a high-level overview. So the output of this algorithm is a optimal maneuver for the ego vehicle in the current state S. In order to compute this, we execute k simulations in closed loop mode. At the beginning of each simulation, we for each non-ego vehicle, we sample the current executed maneuver, its goal, and its trajectory to the goal using the associated probabilities that we computed in the goal recognition step. In the planning part, we select a macro action to try for the ego vehicle, and we then forward simulate that macro action while the other non-ego vehicles follow their sample trajectories from the previous step. Then we enter this block. In this block, we analyze the forward simulated segment and check for things like whether there was a collision with the ego vehicle, or whether the ego vehicle has achieved its goal, or if we have reached the maximum depth of the search. For any of these, we then assign a reward. And if a reward was assigned, we backpropagate the reward along the visited branches in the search using standard RL operators such as Q-learning. Once we've used up our compute budget or run the required number of simulations, we then extract the optimal maneuver to execute for the ego vehicle. So here are our experiments. We did two sets of experiments. In the first set, we have 4 defined scenarios, which you can see here. You can find the details in the paper. But basically, the second scenario here is the one that we used at the beginning of this presentation. And another interesting one is the 4th one here, which is where the ego vehicle has to realize that one vehicle is leaving a gap ahead in order for the ego vehicle to join. The first thing we show is that we achieve robust and accurate goal recognition. This shows you the probability assigned to the true goal of a vehicle in each of the scenarios, and that's over time as we observe more data. And as expected, the probability increases over time and approaches 1. We even observe this in variants of our scenarios where we have significant occlusion. So in these variants, we removed large parts of the observed trajectories, and still the method was able to robustly assign high probability to the correct true goals. And this is shown in the dashed lines. Next, we have a table which shows you the driving times of the different methods. The driving times for the shown in seconds for each of the scenarios. IGP2 achieved significantly lower driving times than the other baseline methods. We have IGP2 map, which is, uses a maximum a posteriori estimate of the goal and the trajectories. Then we have constant velocity baselines and a conservative baseline, which always waits for all traffic to clear. And you can see that we achieve better driving times using goal recognition. Here's a video that shows you IGP2 in action. This shows you the 3 steps of prediction, planning in MCDS, and then execution in the real world. And we call MCDS at a frequency of once per second. So you can see how the goal probabilities change as we observe new data. We approach the junction here, and there's now the realization that this vehicle on the south has left a gap in order for the ego vehicle to join, to merge in, and that's what the ego vehicle then does in a safe way. In the second set of experiments, we had the ego vehicle complete 10 random routes in 2 randomly generated towns. The towns consist of a number of roundabouts and junctions, and numbering anywhere between 2 and 4 lanes, and with randomly generated traffic. And we compare IGP2 to the conservative baseline. And you can see that for almost all of the routes, IGP2 is able to complete the route in a much shorter time. And on the right, you see an example, a route in town number 2. So this completes the presentation. Thank you very much for your attention. Here you see 2 links. One is a link for the paper and the video, and then we're also in the process of producing an open source implementation of IGP2, which will be available soon on the URL shown here. Thank you for your time.